But did it mean that it can't grow extensively? The entropy cannot grow extensively at low temperature.
It means that so I think it is related to what I'm about to say next, but it's related to the degeneracy of the ground state of Hamiltonians, meaning that there cannot be so that's a very good question. Can I just come back to this after I make the next few comments?
Yeah, sure.
The next few comments that I'm going to make may shed some light on it, okay? All right, so any other questions? Okay, so let's try to understand this. So according to Boltzmann, and this is something that is, I'm borrowing it from Mech. Boltzmann's idea of entropy was that the entropy of a system was given by the logarithm of the number of different configurations that system can have given some macroscopic values of its variables. So if I give you the temperature in the volume of a gas, the entropy measures the different ways that the number of molecules can give rise to those macroscopic values, right? And Boltzmann threw in a constant, which is now known as Boltzmann's constant, but this is for this is kind of a dimensional reasons, right? Because in physics, in high energy physics, we actually use a lot of times in cosmology, for example, people use KB as 1. Okay, this is something quite often used, and then energy and temperature will have the same dimensions. Anyway, that's beside the point. So this was Boltzmann's idea, and then so if I have S equals to 0 at, say, T equals to 0, then that means that the number of configurations that my system can have at very low temperature is 1, right? So in other words, this means that the ground state by ground state, I mean where the energy is the lowest. The ground state of our system is unique. Okay? So, generically in quantum mechanics, the energy of a system, okay, is given by a matrix. You can think of as a matrix. It can be an infinite dimensional matrix. That matrix is known as the Hamiltonian, and you know that matrices have eigenvalues. So if the state of a quantum system is described by some function called psi, let me not put the brackets around it, so it'll just confuse people. So it's some function psi, and so this is the eigenvalue equation. So this is some matrix or some operator, and this is some vector, and this is the eigenvalue. And the lowest eigenvalue corresponds to the ground state of the system. Now, generically in quantum mechanics, the ground state is unique. Generically, E0, by ground state, I mean that the function, that corresponds to the lowest eigenvalue of H is unique. Now, what you can do is that usually the Hamiltonian will be a function of parameters such as magnetic field, your masses and stuff like that. Now, you can tune these parameters if you like. And if you tune these parameters, you can have more than one ground state. So you can have, say, size 0,1, size 0,2, blah, blah. You can have a lot of ground states, right? If you have a lot of ground states, then of course, omega will not be 1. It'll be larger. But what happens is that usually in quantum mechanics, there will be interactions in extended systems. Extended systems, different parts will interact with different parts. And a generic result of that interaction is that, this degeneracy, it's called, this degeneracy of the ground states, this will be broken, okay? So I think a lot of this is probably like very new to you, and for those of you who haven't done quantum mechanics. So let me just give you an example, okay? So suppose that our system has rotational symmetry. So suppose that our system is some sort of rotationally symmetric nucleus, right? Rotationally, meaning that it's spherical, rotationally symmetric nucleus. Okay, so because it's a rotationally symmetric, the quantum mechanics tells us that if its angular momentum is, say, L, then there are 2L plus 1 ground states. So, or there are 2 plus L physical states associated to the angular momentum L. Okay, so this is something that comes out of quantum mechanics. You just have to believe me for it. Okay? So if the angular momentum is, say, h bar, if the angular momentum is h bar, that means that the value of L is 1. Then we should have 3, linearly 3 states, psi 1, psi 2, and psi 3. Of course, then omega should be 3, and log of omega is not 0 anymore. But what happens is that, this results comes out of quantum mechanics due to the rotational symmetry. But of course, in an extended system, you have lots of nuclei, and there will be weak interaction between these nuclei, okay? And this weak interaction, what it means is that the rotational symmetry of each of these, nuclei will be broken. So these 3 states which had, say, the same energy, because of this, perturbation, their energy will be slightly, different. Okay, so this happens because the rotational symmetry is going to be broken. And therefore, what we will have is that we will have a unique ground state. Okay, and I believe that this is basically what, what is, involved in saying that S of t over n goes to 0 at t equals to 0 and n equals to infinity. Okay, so if this were not the case, then the more and more nuclei I added, the more and more states would be added to the ground state, and the entropy of the ground state would be quite huge. Okay, so I think this is basically the reason why, for extensive systems, we are saying that the entropy density has to go to 0. Okay, does that make sense, Saif?
Yeah, I think so. I'll probably have to watch it through again on the recording.
Okay. Yeah, it's you know, so the interesting thing about the third law, Nernst's law, is that it comes from quantum mechanics. Okay, that quantum mechanics really gives an absolute scale to entropy. And so if I now look at, say, the classical result of entropy, so suppose we have SB minus of SA, and you can show that this is measured by the heat capacity of your system. Now, if I look at an ideal gas, for the ideal gas, the heat capacity is given by N of Kb. And we see that in that case, the entropy does not go to zero at T equals to 0. And the same for, the Dulong-Petit, formula for a solid. And all of these things, what they're saying is that classically, the entropy does not go to 0 at T equals to 0. Okay? So classically, as T goes to 0, S of T does not go to 0. So the third law is a quantum law. It is not something that comes out of the third law classically. Okay?